Okay, so now we would like to proceed into the modeling step, and we would like to have an explicit relation between stress and strain such that when we are given the value of the strain, we can predict the corresponding value of stress, or for that matter, for a given amount of deformation, I can tell you exactly how much load you need to apply to reach that deformation. So we are going to employ two models, and in both of these models, the difficulty stems from the fact that in reality, the metals or many polymers display hardening of some type, which renders the stress-strain curve non-trivial, because if it were elastic, perfectly plastic, then for any given amount of strain, I just need to look at whether it's in the elastic or in the plastic region. If it's in the elastic region, sigma is E epsilon. If it's in the plastic region, the stress never changes and is equal to the yield strength of the material. So elastic, perfectly plastic poses no difficulty. The difficulty is when the material continuously hardens so that the stress keeps increasing. And that's where we are going to employ two models. The first one is going to be is called the elastic power hardening model. Okay, so in the elastic power hardening model, what we start with is a description of the relation between stress and strain, and that description is constructed through the following steps. First, we say that, well, if I am in the elastic region, so in other words, if stress is less than or equal to sigma naught, then that's the elastic region. Then I know that, well, the relation is simple and sigma is equal to E times epsilon. Now, if I'm in the elastic region, the stress is not a constant anymore, and it's not equal to E epsilon because it's not a line, it doesn't change linearly, plus it's not a straight line at least, plus it is continuously varying in magnitude because the material hardens. So what I want to have probably is some simple relation that is able to capture that, and the simplest thing one can think of is a constant times the strain raised to some power, and let's call that power n1. So if we are in the region where yielding has occurred, or you are beyond the point of yielding, then you want to capture the ever-increasing behavior of stress with respect to strain. So you put an exponent of strain multiplied with some constant, and therefore you capture hardening. And in particular, we have a power hardening relation because of this exponent. Okay, now remember that whether you are in the elastic or plastic region, it doesn't matter. Sigma is always equal to E times epsilon E, the elastic portion of the strain. That's something that we will keep in mind. It's valid in both regions, both elastic and the region beyond the elastic zone, in the plastic power hardening zone. In the elastic region, epsilon is of course equal to epsilon E. There is no difference, but that's not the case in the power hardening region. Okay, so here E is the Young's modulus, that's clear, but we have now two new material parameters. These material parameters are modeling parameters, and we have just two parameters, H1 and N1, so we have only a limited minimal set of parameters that captures the essentials. And having said that, at this point you may want to just roll back and have a look at that modeling idea I talked about earlier when we tried to replicate data points with a good model that is able to fit that curve. So that model is going to eventually have some free parameters. This is a very simple model with only visibly two parameters. It turns out there aren't two, there's less. But in any case, we don't know yet the values of these parameters. We have to determine them such that eventually the stress-strain curve that is predicted by these two equations is able to replicate the data as closely as possible. So determination of those parameters is an issue on its own. I'm going to solve a simple example. Well, this example is not simple, but I'm going to solve it in a simple manner to demonstrate the idea of about the determination of these parameters. So first of all, let me mention that the parameter that we have, the exponent n1, obviously, first of all, is something that is less than 1, right? So if I want to write a relation between stress and strain beyond the point of yielding, if the exponent is larger than 1, the curve will go like this. If it is less than 1, it will go like that. If the exponent is 0, it will be a constant. Okay, so exponent of 0 would be perfectly plastic. If it's larger than 1, it's not realistic. It should be less than 1 and greater than 0 so that we have some realistic replication of experimental behavior. So the typical values, it doesn't have to certainly larger than 0 and less than 1, but typical values lie in that range. The value of, or the name for n1, sorry, is called the strain hardening exponent. Okay, h1 is a constant. Let's not give it a name. Okay. All right, well, so at this point, what I seem to have is a model that is able to predict what happens in the elastic and plastic regions, provided I know the values of H1 and N1. But I also need to know the value of the yield strength of the material in order to apply this model, because the model has two legs. I need to check, first of all, if it's in the elastic zone. If yes, I can use that relation, but if not, I need to use this relation. So you give me the value of strain, I can still predict the stress. That was our purpose, remember. That's our modeling target. But to do that check, I need to know the value of sigma naught. So at this point, take a second by pausing the video really, and think about how I could determine sigma naught. Because it turns out, something that does not need to be independently supplied. It is something that comes out of the parameters that I have here. Okay. Alternatively, if sigma naught is given, not all of the parameters that I see here, in particular h1 and n1, are independent from sigma naught. They are, it turns out, functions of sigma naught. So take a few minutes and think about whether you could determine sigma naught given E, H1, and N1. Okay? Now, I'm going to go ahead and give you the answer. And the answer is based on the plot of these two individual behaviors. Now, on the left-hand side, well, not the left, but the first one is the elastic one. Epsilon versus sigma is what we're trying to draw, and that is the elastic portion of the plot. And the elastic portion says that sigma is equal to E epsilon, always. Now, we know that's not true because after a while, we'll go into the elastic region, and I will not have really sigma a linear relation, but a deviation from that. Now, the second model is a power relation. You give me the value of epsilon, provided I know h1 and n1, n1 being less than 1, I can tell you what sigma is. If I plot that relation, it turns out with realistic values of h1 and n1, what you're going to observe, and let me draw that in a slightly different way, you will see a function or a curve that looks like this. Okay? I'm drawing it only to a certain extent, certainly to a region before nicking occurs, for a reason that I will comment on shortly. So this here is elastic. This curve here is power hardening. Now, well, what is the yield strength? Well, what we know is that one model is valid up to yielding, the other model is valid beyond yielding. but they have to agree at a point where yielding occurs, because both of them have been defined to be valid at the point of yielding. That's our equality sign here. And that point is exactly that point. So the point where the two curves intersect each other must be associated with the yield point. And in particular, we will have a yield strain of epsilon 0 and a yield strength of sigma naught. So the real prediction of our model is that if the stress is less than the yield strength, we take the elastic portion of the curve. And if the strain is such that the stresses are larger than the higher than the yield strength, then we take the power hardening portion. So the blue curve is our model. Okay. Well, now that gives us an idea about how to calculate the yield strength. Now, the yield strength, sigma naught, can be predicted in two ways. One, it is equal to E times the strain at yielding, that's the elastic portion of the curve, but also the power hardening relation is supposed to give us exactly the same value. Epsilon 0 to the power n is supposed to give us, to the power n1, supposed to give us the same value of stress. And from these relations, what you can do is you can first of all solve for the value of epsilon 0. And epsilon 0, it turns out, go ahead and do that yourself, and you will find that epsilon 0 is E over H1 to the power 1 over N1 minus 1. Okay. And you can then take that epsilon 0 value, plug it either in there or in there. You will get exactly the same value of sigma 0, and sigma 0 will come out to be E times H1 over E to the power 1 over 1 minus N1. Okay. So here what we see is a interesting outcome. We see that the yield strength of the material is not an independent modeling parameter. Young's modulus is something we need to determine. It's a material parameter. H1 and N1, if they are material parameters, then sigma naught is not. Alternatively, if we are somehow given sigma naught as beforehand, let's say together with E, then sigma naught is given, E is given, only H1 or N1, one of the two, can be supplied, because this relation always needs to be satisfied. If I know sigma naught and E, and let's say I know what H1 is, N1 is something I can determine from this equality, and so on. So overall, when I look at this model, apart from the value of the Young's modulus, I have only two material parameters, H1 and N1. Sigma naught is not an independent parameter. So this is the elastic power hardening model. The elastic power hardening model, notice that it's predicting a distinct sharp corner, which is very clearly observable, and it indicates yielding, right? We know in experimental observations that this is not quite the case. We don't have a sharp corner, we have a smooth corner. So the next model is going to go ahead and address that. Now, the second thing I'd like to comment on is the question of what the plastic strain is. Earlier, when I was talking about the modeling aspect, I said that what we really want to implicitly address is what the value of the plastic strain is, because sigma is always equal to E times epsilon E, and epsilon E is the total strain minus the plastic strain. You give me the value of strain to calculate the stress. I need to know what the plastic strain is. So notice that this model is taking a slightly different perspective. It predicts the value of the stress in the plastic region also through the overall strain. So that's the choice that the modeling is making. But plastic strain is still on the background and something that we can extract from this model. In particular, notice that the plastic strain is easily extractable because epsilon E is sigma over E, And from that, I can calculate the plastic strain to be epsilon minus epsilon e. Remember, this relation is always valid. So you give me the value of the strain, I know the value of the stress, divide the stress by the Young's modulus, I know what the elastic portion of the strain is, subtract that from the overall total strain, you get the plastic strain. So the plastic strain is still playing a significant role, but on the background. And finally, if you like to use this model, with the true stress strain curve, all you have to do is you replace the epsilon with epsilon tilde and sigma with sigma tilde, and the rest of the model works exactly as I have displayed here. And in fact, this is something you really have to do at or beyond the point of necking, because remember, the true stress strain curve always increases, whereas the engineering stress strain curve will start decreasing after a certain while. It is the true stress strain curve that continuously increases. And this relation is predicting an ever-increasing trend for stress with respect to strain. So in other words, this strain in terms of engineering stress strain wouldn't work because engineering stress strain starts to dip down after a certain while, whereas this true one will always keep increasing. So that relation towards the point of necking and beyond the point of necking is certainly going to be used with true strain versus true stress, because only that one makes sense. All right, so presently we are looking at a point that is in the vicinity of yielding, and in that region we know that if the deformations are sufficiently small, true stress and strain are almost the same, and hence true the true strain and engineering strain are almost the same, and therefore the true stress and the engineering stress will also be almost the same, and therefore that's what I have drawn on the plots over here. So that was the first model. So now we're going to go ahead and look at our second model, and I'll try to squeeze everything onto the same paper so that we see everything here clearly. Okay, so let's draw a line here. Sorry. And so we're going to look at the second model. And the second model is called the Ramberg-Osgood model. Okay. Now, the Ramberg-Osgood model is quite different, actually. And the way it works is, again, it builds a model for stress in the following way. Again, you can just go ahead and replace the engineering quantities with true quantities to make use of this model in exactly the same way that I'm about to write. And what it says is that, well, you can first of all always write E is equal to epsilon E. There's no argument about that. That's experimental observation. Unloading is always elastic, and the slope is equal to the Young's modulus. So that's always true in the elastic or the plastic region. What it also says, strangely at first sight, is that also always it's going to predict the total stress to be the plastic portion of the strain, which I don't know beforehand. Neither do I know the elastic portion of the strain beforehand. Remember, that's a part of the modeling. It predicts that simultaneously the stress can be written as such in terms of the plastic strain, also through some sort of power relation. Okay. And again, we have N as our strain hardening exponent and H as some constant. Okay, so that's our Ramberg-Osgood model. Well, you give me the strain and I'll tell you what the stress is. That's my goal. But you give me the strain, I don't know the elastic and plastic portions, and therefore I cannot tell you what the stress is. So I seem to be stuck at first sight, but we don't panic and just go ahead and first calculate the elastic portion of the strain, which is simply sigma equals sigma over E. And we can also extract from this relation, this proposed relation, the plastic portion of the strain, which is simply sigma over H divided raised to the power 1 over N. And then I know that the total strain is equal to the sum of the elastic and plastic portions, and therefore the total strain is equal to sigma over E plus sigma over H to the power 1 over n. Okay. Now, this is a strange relation because it sort of works in the reverse manner. My goal was you give me the value of the strain and I tell you what the stress is, but now I have a reverse relation. The relation works naturally in the reverse direction. You give me the value of stress and I can tell you what the value of the strain is. Well, not too bad actually. It's still a relation, it's a functional relation, and in fact I can go ahead and plot that relation. So now not epsilon versus sigma, but rather sigma versus epsilon. Sigma is on the x-axis, and if you do that plot, what you will observe is that that plot will look like this. Okay, all right, okay, so that's exactly what that relation gives us. Now, is that useful? How does that help us? Now, the way it helps us is as follows. So first of all, if you would like to determine the value of stress for a given value of strain, you can still do so. You give me the value of strain, I know the left-hand side. If I know the values of E, H, and N, I can go ahead and determine the value of sigma. It's a nonlinear relation between sigma and epsilon, but if I know the left-hand side and these parameters, then it's a nonlinear equation for sigma and I can solve for it in some manner. So still, conceptually, the relation certainly works numerically as well, but it's just not easy to solve for. But we have realized our target nevertheless. Another question to ask here is, well, what is the yield strength? Now, the yield strength is something we need to think about, and the best way to think about it, I think, is to go ahead and plot this relation in our classical view. So I'm just going to go ahead and flip these axes, and I'm going to draw the way the curve looks with respect to our usual understanding of the stress-strain curve. And this is the way it looks. I've just flipped the axes, so flip that picture, and that's the way it's going to look. And just like I see in that picture, also in that picture, there is no distinct yield point, unlike the elastic power hardening model. There is no distinct corner, and that's good in some sense, because that's something I also don't observe in experiments. And therefore, it seems that Ramberg-Osgood model is resting on the assumption that plasticity is, or the onset of significant plasticity is not very easily distinguishable. It's not a on-off phenomena as it is here. Up to that point you have no plasticity, beyond that point you do. Instead, it proposes that there is plasticity always, even from the outset. So you give me a very tiny amount of stress, there will be a certain amount of plasticity according to this relation between stress and the plastic strain. And that proposal causes this elbow, let me say, instead of a corner, to form. So the Ramberg-Osgood model proposes that there is plasticity from the outset and that replicates experimentally observed behavior. Now, does that proposal make sense? It does make sense, because in reality what happens is that you build such a specimen, but this specimen is not perfect. Somewhere throughout the specimen inside, let's say at that point, and let me try to mark it with a red point over here, at that point we are going to have inside perhaps some tiny void, some tiny bubble of air, let's say, that's going to cause that's essentially called an imperfection. It's going to cause stress concentrations around it, as you will remember from ME 231. As soon as you have a stress concentration, and depending on the shape of that void, those stress concentrations can be very, very large. And in fact, if the void is so narrow that it's almost like a slit, it's almost like a crack, the stress concentration factor is large enough to cause yielding even at tiny stresses. So if the stress is very, very small, still you will have some plastic strain due to that stress concentration, and something that is embedded in some sense in the Ramberg-Osgood model. But that amount of plastic strain is there, however, it's not appreciable. The plastic strain starts to become appreciable when plasticity occurs not only in the vicinity of the imperfections, but across the whole interface, and that's what I'm drawing with blue here. So these are some vague discussions, but essentially the idea is small imperfections will cause some plasticity even at small stresses, and that's reflected in the Ramberg-Osgood model, but appreciable plasticity is defined as being in some sense plasticity that occurs not only in the vicinity of concentrations, but in some way over the whole cross-section of the specimen. And that idea now goes very well hand in hand with our previous discussion of identifying the yield strength when there is no visible corner. We said that the yield strength is the strength of the material or the stress when there starts to become appreciable plasticity. This is not appreciable plasticity. It's only occurring in the vicinity of, say, stress concentrations. Appreciable plasticity is defined in our case for these types of stress strain curves as or through the 0.2% offset method. So in this particular scenario, the yield strength is an outcome of the model. It's not something that needs to be satisfied by the parameters from the outset. You give me the parameters, and then what I do is I throw in a 0.2% offset, and where that 0.2% offset that's parallel to the, or it has a slope of E, where it intersects the stress strain curve, it's my yield strength. Well, what is therefore the yield strength? The yield strength is the stress at 0.2% offset. What is that offset? That offset is plastic strain. Remember, what we've said is we unload at some point if there is appreciable plastic deformation, and that appreciable amount is 0.2%, then that stress is the yield stress. And therefore, the plastic strain at that point is 0.002. That's what we have to input here, not percent, but the actual value. And when it is raised to a power n and multiplied by h, it should deliver me the stress, and that stress, as defined through the 0.2% method, is the yield strength of the material. So that's how you find the yield strength. So therefore now we have two models, one with no on-off, two relations that are always valid, and it gives us a behavior that is quite similar to experimentally observed stress strain curve, and another one with a distinct yield point that is closer to our understanding, closer to our idealization of the stress strain curve. It works in an on-off manner. This one is on up to the point of yielding and then off. This one is on, but both models eventually are models. They are good and valid to the extent that they can replicate experimental data. And now what we would like to do is we want to go ahead and apply these in the context of an example.